So this is going to be the last lecture of this chapter, radiation and matter, or dual nature of radiation and matter. So what we're going to learn in this, wave nature of a matter. Like a matter is also behave as a wave nature, and the proof is going to be done by the Davisson and germer experiment. Okay, so there is an experiment and there is a hypothesis, de Broglie, or also known as de Broglie hypothesis, in which for any particular matter wave, okay, for any particular wave which is originated from the matter itself, there is a relation between lambda and momentum. Basically, it is coming from uncertainty principle. What is the uncertainty principle? We are going to discuss in this, but a small discussion about it. Uncertainty principle states that whenever you want to find the position and momentum both simultaneously, so you can only find one because of wave nature of you can say particle, or because the wave nature states that. How it is going to be relevant? For example, as we know, wave is what it is, a continuous motion of energy, right? So whenever a wave is moving in this way, so either you can tell about the momentum, which is a kind of energy, momentum, how it is kind of energy, p square by 2m, and either you can tell about the displacement, del x. Okay, so here for the wave, del x can be, or displacement can be, or position can be treated as a lambda. Lambda, what it is? Wavelength. Is this clear, everyone? Is this clear, everyone, beta? Okay, just a minute. Give me a minute. Hello, 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 hello. Am I audible, visible now? Okay, so let's start this. As this is a reflection, as we know, electromagnetic wave propagation and direction means electromagnetic wave is a kind of a wave which generated by the electric field and magnetic field, and we know each particular matter is made up of electron or charged particle. So in each particular, first of all, just turn on your cameras first. How many times I need to tell you this? Am I teaching to a blackboard or what? Or a black screen? Is this the thing I need to tell you again and again? Tell me, beta, everyone. Huh? Is this the thing I need to tell you again and again? You need to open your cameras. Okay. So, just so many things I need to do today. So this is a reflection, just electromagnetic wave. We know each particular matter is made up of a charge particle, okay, equal number of charge. So obviously if the matter is going to be moved, or you can say charge particle is going to be moved, so it is going to create a magnetic field, and whenever we have a magnetic field and electric field all together in a perpendicular direction, so the propagation of direction is going to be the perpendicular to both, and a wave is going to be generated, that is known as EM wave. Okay, now we already done this Einstein photoelectric equation in the previous class, so just a quick recap about it, or recall. When a substance absorbs electromagnetic radiation, electrically charged particles are emitted from inside it, resulting in the photoelectric effect. The phenomenon of emission of electrons by certain substance, that is metal, when it is exposed to the radiation suitable frequency, is called photoelectric effect. Okay, and the emitted electrons are called as photoelectrons. One significance in Einstein photoelectric equation, we always write kinetic max, where hv is the incident energy and theta naught is the work function. In general photoelectric equation, we can write in this way, which is Ke plus W naught. Here W naught is work function, K is the kinetic energy of photoelectrons, and E is basically this written thing, same, E equals to energy, incident energy, H nu. Okay, is this clear, everyone? So this equation is called Einstein photoelectric equation. Moving ahead, this is the main thing. You can say dual nature of a matter. As we know, matter have initially or till now we know just just the particle nature of a matter, because we can observe, we can see that thing as a particle, right? But as a light, it is have a dual nature, a particle as well as a wave. In a same scenario, each particular matter have a dual nature also, and that is given by the de Broglie equation and de Broglie hypothesis. So who is this? This is de Broglie is a scientist. So in 1924, Louis de Broglie wrote a doctoral dissertation. What is the dissertation? Whenever you done masters, sorry. So in masters, you need to find something unique. That is known as dissertation. Or when you do PhD, this doctoral dissertation means in PhD, what we need to do, we need to discuss, we need to discover, invent something which is undiscovered till then. So in that particular PhD doctoral paper of his, in which he proposed that since the photons have wave and particle characteristics, like photon can behave as a particle and wave, perhaps all forms of matter have waves as well as the particle properties. Means, like when photon can behave, like photon can have a dual nature, particle nature or wave nature. In a same sense, each particular matter can behave as each particular matter can behave as both of things, particle nature as well as particle nature as well as wave nature. Is this clear, everyone? So this is called the dual nature of a matter. Dual stands for here two. Dual means beta two. Okay, like in early ages of smartphone, we have a dual SIM, or right now we have a dual SIM. So what is the meaning of dual? Dual means two only. So this is called dual nature of a matter, according to which what it is, a matter particle moving with a velocity v can be treated as a wave of wavelength lambda. This is called the de Broglie wavelength, and it is defined by lambda, which is h by p. H by p is basically, okay, this is your called de Broglie. Sometimes it is also pronounced as a de Broglie. In general, you can say that de Broglie. So de Broglie wavelength is h by p, h by mv. Okay, unless the matter is not going to move. So obviously the charge particle is not going to move, and when charge particle is not in motion, in general charge particle always is in motion, but we consider a motion whenever a particle, or you can say a matter, is moved externally. So then in that scenario, charge particles are in the motion, charge particle are in the motion, give you magnetic field. Charge particle itself give you electric field, and due to electric field and magnetic field, we have a wave kind of structure. Clear? Where mass, is this clear, everyone? Is this clear, beta, everyone, what I'm saying right now? Okay, where m is the mass of a particle, or the waves are called the matter waves. Further, with the analogy of photon, the frequency of matter is mu e by h. Okay. In the previous case, we also find that this frequency of photon is E, energy by h. So in the same analogy, the matter waves have a frequency nu, or you can say frequency f is E by h. Is this clear, everyone? So these two equations are important one. Direct question you can see from them. Clear, beta? Direct question. Okay, moving ahead. Lambda is smaller for a heavier particle, obviously, because this is the general thing. You can keep it in your mind. H by p equals to h by mv. So the heavier the particle, now what it is, now you can see that why we cannot see the wave nature in day-to-day life. So from this simple equation you can find it. See, in day-to-day life, the matter, or you can say mass, can be into the consideration of few kilograms. Clear, everyone? You can say 10 kilogram to 100 kilogram. And the velocity is going to be very narrow. So for that 10 kilogram to 100 kilogram, this h, as we already know, this h is what it is. Beta, it is 6.63 into 10 to the power minus 34. So how you can see something which is 10 to the power minus 30, even with the help of some instrument. Got it? Why we can see the waves for quantum phenomena for very small thing, for proton or electron mass. Why so? Because that is very easy to understand. Because the mass of electron, we everyone know, mass of electron is what it is. Mass of an electron. Mass of an electron. How much it is? Mass of an electron, ME, is 9.1 into 10 to the power minus 31 kilogram. Is this clear? Now you can see if I put this, and if I say velocity is some, you can say very, very high. Got it? Then you can observe this particular wavelength up to the range of micrometer or up to the range of several nanometers. Several nanometer means a few hundred nanometers. So it is difficult even to observe. You cannot observe with the naked eye even, but it can be observed with the help of some instrument, microscope and so on. Got it now? So that is why we can only see the waves or matter waves for a quantum phenomena for a very small particle. Is this clear, everyone? What I am saying, is this clear now? Clear? Beta, yes, no, something, anything. Is this clear or not? Other than Yajira, you are also taking the class. Pavan, Sudarshan, Sai, Vishwanath, and Darshan. What are you doing? You are not in this class or what so? Okay. So in the same example, lambda is smaller for a heavier particle, large m, for more energetic particle, large v. For example, the de Broglie wavelength for a ball of mass 0.12 kilogram, which is, you can say, 1200 or 1200, I'm saying 120 gram, moving with a speed of 20 meter per second. So P is going to be this much, and now you can see the effect. Lambda is going to be the order of minus 34. Even with the help of some instrument, we cannot see that. So that is why in day-to-day life, matter can give us the wave, but we are not able to see this. So that is why we can only observe the one nature, the particle nature of a matter. But when we are go into the quantum range means in electronic range even. So this is your quantum range. Quantum stands for very small, okay, or atomic range even. This is even atomic range, okay. So when we are shift into the quantum range, so the mass is very, very less, then we can able to observe. So this wavelength is so small that is beyond any instrument. Even you cannot find with any help. We cannot find this wavelength with the help of any instrument. This is the reason why macroscopic objects in our daily life do not show wave-like properties. On the other hand, in the subatomic domain, this is your subatomic domain, the wave characteristic of a particle is significant and measurable. Because the mass of a photon is massless, the mass of a proton is this much, you can say 1.67 into 10 to the power minus 27 kilogram. But the mass of an electron is minus 31 kilogram. So that range is only and only appreciable to which level? Micro level. And we can observe anything in the micro range with the help of microscope. Even in the nano range or 10 to the power minus range, we can observe nowadays. Clear, everyone? So that is why we cannot able to see the wave like characteristic for a day-to-day life. Now, for a particle of mass moving with a velocity, the kinetic energy E k is going to be half mv square. In the same sense, v, here v is velocity, 2 ek by mv. From this particular relation, if I am going to put the v here, the value of v, basically what we are doing, from this equation 1, we are putting the value of v in our de Broglie wavelength and finding the relation with the mass and energy, or basically kinetic energy only. So as we know, that is H over mv. So I am going to put the value of mv. mv is what, beta? In simple word, you can put the value of mv direct. mv is momentum, and we know momentum, you can find it down, or you can write it down, momentum 2 ke, which is kinetic energy, divided by m. This is our momentum. How so? As we know, kinetic energy ke is nothing but half mv square, multiplying and divided by m. So this convert into the m square v square. So we can write simply kinetic energy p square by 2m. Okay, so if I want to find the p, so that is under root of 2 ke by m. Got it? Is this clear now? Is this clear with everyone? Something I'm doing wrong. Wait. 2 ke into m. How it is clear? That is correct ratio. Okay, wait. So from this particular previous relation, just remove this. Yeah. So now you can see P is under root 2m ke. Okay. This is my momentum. Done. And we know from this general relation using de Broglie wavelength, that is h by p, or basically h by mv. Got it? So directly you can put the value of p, which is under root 2m ek or ke, whatever your. So you can find this relation in this sense also, 2m ek, because kinetic energy. Okay, so we can prove this relation, equation number 2 also. Is this clear now, everyone? Either you prove in this way just by putting the value of v, velocity, either you can directly put the value of p, because mv is p, momentum. Clear everyone this thing? Is this clear now with everyone? Now, as we know, we can put the kinetic energy into the EV form. EV form means charge into what? Volt. Good evening, sir. Sorry for. Okay, beta. Okay, we can find kinetic energy into QV form from the photoelectric equation. We know kinetic energy can be stopping potential into charge, so we can use this in the next page. Okay, so you can see that for a charged particle of charge q accelerated from rest through a potential difference v, the work done is qv. Okay, how this everything is going to be correlated? As we know, work done can be stored as a kinetic energy or a potential energy. And from the definition of potential, we know work done is, from the definition of potential, we know potential is work done divided by charge. So from this, q into v. So just putting here the value of work done. Is this clear, everyone? This relation is clear now, but I write it down on the extreme left, this one. Okay, so now when I need to put the value of kinetic energy ek, I can put qv also. So this is one of the most important relation. What is going to be, just a minute, let me write it down. How they ask, they just give you the potential for an electron, and mass of electron you automatically know, and charge of electron you automatically know, 1.6, and then h you also know. So just by providing one single thing, potential for an electron, potential for any particular particle, for which you know the charge and mass altogether. If the photon, so the photon charge is +1 and it is massless, so it is not going to give you the lambda. But for a proton, if I'm just giving you, find the you can say wavelength for a proton of potential something means 2.3 volt. Okay, so I don't need to give anything else, everything you know. But at that time you don't remember, or you don't know even this formula, because you going to be confused, and every student going to be confused just with the help of potential. How can I find it? So this relation is going to be help you out, because if I give you the mass I mean, obviously we know the mass of a potential, that is going to be 1.67 into 10 to the power minus 27 kilogram. Okay, and if I just give you the potential of a proton, so that is, you can say, suppose 4.5 volt directly. Even it is very high, we give you into the terminology of EV, electron volt, but just I directly give this. And we know the charge of a proton is going to be plus E. Okay, one electronic charge, positive. And then mass we know, everything we know now. H we already know, it is a constant. Okay, then we don't need to know, then we don't need to get anything to find this lambda. Clear na? So as you can see, it is quietly, it is directly written over here. This relation holds for any charged particle like proton, electron, or for even number of charged particles. Clear, everyone? So this is very, very important. Is this clear, beta, everyone? Good. Okay, after even the sentence is even charge ions, where m corresponded to the mass of the charged particle, of course, where v is very large, say in kilovolt, so that the speed of the particle becomes close to the speed of light. Such an equation is not applicable. You will learn about other effects in such equation in higher class. Means what it is written over here. Instead of simple electron, proton, or even charged particle, if I am going to give you the ions. So beta, for ions, the potential is going to be in terminology of kilovolt or megavolt. For kilovolt or megavolt, the kinetic energy is going to be very, very high, right? If I give you this kilovolt or megavolt. So this V, because kinetic energy is half mv square and this qv. So beta, so V, here V is velocity. So velocity is going to be turning to some order of c. What is the meaning of this? You can say 0.7 c, speed of light. So when it is going to be speed of light, so we are going to see some another effect, and that we are going to learn in the higher class. We cannot use this particular relation for higher volts. Why so? Because this is going to be, and when any particular particle is going to be move with this speed of light, so we are going to see some interesting and new effect, which is going to be understood or is going to be teach you in the higher colleges, or you can say STR basically. Okay, relativity theory. Even the mass is going to be changed. I tell you in the previous class. Okay, means mass of a particle is going to be changed, and so it is going to be done. Clear with everyone? We have one important one more important relation related to this. Now it is very, very important. You can use it directly. Okay, what it is? Let's see this. For an electron moving through a potential difference V, given in volts. So for electron, what we can see, lambda is h by 2 me, that is E. Charge for an electron is E, that is E. Okay, and volts simply. So when we put everything all together, what we get? Lambda in mm, it is not mm, it is going to be nm. Wait. 1.288 10 to the power 31 sorry, 31, and this is going to be 19. So 31 and 19, 40 and 40. Wait, it is not mm even, it is nm. Nm stands for nanometer. Okay. 31, 34, 14, 34 minus 20, it is going to be, just order I am saying, see, under root of power 10 to the power minus 31 minus 19 minus 40. So that is going to be 10 to the power minus 20, and whenever it is going upward, so it becomes 10 to the power 20. Okay, so 20 and then 19. So it is in 19. So angstrom, you can remove this because this is perfect. You don't need to write this relation. Even this is not. Okay. So lambda is of that much order. And now you can see even for an electron, how less it is. 10 to the power minus 19. Very, very small, even for a electron. Because this electron is not moving with higher potential, not moving with higher velocities. Okay, if I put megavolt, so 10 to the power 16 is going to be done, and then it is come into the range of few picometer and so and so. Clear everyone? This one. Is this clear, beta? So this relation is very, very important. This one. Okay. So directly you can use this. Now moving ahead, this is your Heisenberg uncertainty principle. I already teach you this. You can say I not teach. I already give you a hint about it. This one is also important one. So what it states that if del x is the error in the position measurement, P is the error in the measurement of momentum. What is the error basically? If you find the momentum of a wave at two particular points, so del P is going to be P2 minus P1, or sometimes you find this momentum at the same point but two different times. So that is going to be the error. In the same way, del x is going to be the error for a wave kind of thing, for a matter wave x2 minus x1. Okay, two different position, or maybe two same position at a different time. So then del x into del p equals to and greater than h by 4 pi. This is your Heisenberg uncertainty principle. What it states that if you want to find change in position and change in momentum simultaneously, so you cannot find. Since momentum p equals to mv, okay, Heisenberg uncertainty principle formula can be alternatively written as this. You can put the value of lambda change in momentum, that is mv. So del m into v, or it is going to be under the bracket. So del m into del v. So where del v is the error in the measurement of the velocity, and assuming mass remains constant during the experiment, so del x into del v is h upon 4 pi m. Okay, simple thing. If for a matter wave, okay, if for a matter wave we are trying to find, for a matter wave we are trying to find, you can say that change in position and change in velocity, so we cannot find it. Why? So you are going to see on the next page. Is this clear, everyone? Is this clear now? Till now, this is your Heisenberg uncertainty principle. Uncertainty stands for if we are trying to find position or momentum simultaneously for a matter wave. What is a matter wave? When a particle moves, it creates a matter. It creates a wave. Okay, in this way, or you can say simply electromagnetic wave. So for that particular matter wave, if at any single position, at this particular A position, suppose this is a matter wave. Okay, at this particular position A, if I am trying to find the change in del x from here to here and change in velocity, same at from this particular point, you can say A to B. So I am not able to find it simultaneously both. That is the uncertainty principle. We are uncertain. Why so? Because matter wave or any particular kind of wave moves continuously. So whenever any particular thing moves continuously, so you can, or any particular observer or anything can be try, or you can say anything can be observed one single thing at a time. Simple logic. Okay, means if there is a car is going to be moving with very high speed. So either you can tell it is passes from this particular pole, this particular pole, this particular pole, or either you can say it is moving somehow with a speed of 100 kilometer per hour or 150 or 80 kilometer per hour. Got it now? You cannot say, you cannot tell both of the, you can say simultaneously both. Simultaneously means at the same time. Like it is passes from this particular pole with this speed, this particular pole with this speed, this particular pole with this speed. No. In the same sense, it is here written over here. Okay. So moving ahead, accurate measurement, more detail wise, accurate measurement of position or momentum automatically indicates large uncertainty, error. Uncertainty is basically error in the measurement of other quantity. For example, applying Heisenberg uncertainty principle of an electron moving in an orbit of an atom. H is this, we know this. Mass of an electron we know. So if we are trying to find a position and velocity of a charged particle, which is an electron moving even in an atom. So we know, obviously, suppose this is your atom. Okay. So even in this small periphery, we cannot find it. Why so? Because of this particular principle. Because of this particular principle. Okay. So suppose this is your nucleus and this electrons revolving here, here, here. Basically, this picture is for standard 10th even or 8th. In general, it is not. You are not going to see this kind of picture, sphere or spherical something. But to make calculation easy, we can say smallest shell is a spherical shell and electrons move in a sphere. Got it now? But they can move in any particular kind of sphere. Just for a little treatment, this sphere maybe, this sphere maybe, this sphere maybe, this sphere maybe, any particular kind. Okay, but for general aspect, we make simple look-alike sphere. This one. So even for electron, as we know, electron can move with some any velocity, but it is going to be found in that spherical periphery. Still, you can see the 10 to the power minus 4 meter square per second error is going to be done. Okay. So del x into del v going to give you 6.620 or 6.63 10 to the power minus 34, and that is going to be 4 pi 10 to the power minus 31, because we know this del x into del v, del x into del x into del v is nothing but h upon m, 4 pi m, equal and greater than. Okay, so we take equal thing and then we can put it down. So 10 to the power minus 4 order of uncertainty or error you can get. If the position of the electron is measured accurately to its size 10 to the power minus 10 meter, then the error in the measurement of its velocity will be equal to or larger than 10 to the power 6. It is 1000 kilometer per second, and you can say that much wrong it is. Clear? So Heisenberg principle applies to only dual-natured microscopic particles and not to macroscopic particles whose wave nature is minimal. Means we can only find this particular thing for the wave nature of particle, or for the particles which shows wave nature easily or clearly. If we trying to do so, this Heisenberg uncertainty principle for day-to-day life, or you can say for a ball or for something object, so we cannot do that, because these macroscopic objects cannot generate a wave, cannot show the wave characteristic or wave nature of a particle or matter waves in general. Got it now? So in this way, we cannot use that. So now this is your first question related to this. Do that, and then we are going to discuss. After there are 2 questions, and then after the 2 questions, I'm going to give you a break, and then there is a photocell. Photocell we already done, and we are going to discuss Davisson and germer experiment in great detail in the next half. Okay, everyone. So do this question. This is very easy. The lifetime of an excited, the lifetime of an excited state of an atom is 3 into 10 to the power minus 3 seconds. What is the minimum uncertainty in its energy? Okay, one important aspect I want to tell you here. As we have uncertainty in position and velocity, clear? Or just write momentum, because momentum you can understand very clearly. In a same sense, we have uncertainty in energy and time also. Change in energy into change in time we cannot find simultaneously. In a same sense, we have this particular relation for angular aspect also. What does it mean? Change in theta into change in angular momentum we cannot find simultaneously. Okay, so if you see this relation and questions on these relations, don't panic first of all. Got it? Is this clear now, everyone? So the second relation, which is change in energy into change in time, we need to use in the given question, which is on the next page. And that is same. Clear? Good. Then use it. Life time of an excited state of an atom. So that is change in time. Okay. You need to find the minimum uncertainty in energy in EV. So now you can do that. EV is basically electron volt. Okay. So whatever the energy you get, first of all, you need to divide it with the electron. What it is? 1.6 into 10 to the power minus 19. So do that and tell me the correct answer. Okay, do this. Find energy in joule first and then divided with the electron, which is 1.6 into 10 to the power minus 19. So you can get this relation. Tell me, beta, what is the correct answer? Or should I need to explain this? If I need to explain this, just let me know, beta. C. Everyone got C. Exactly. C is the correct answer. And how we can do this? Let's see this. C. Time and energy are conjugate pairs. Okay, these are also known as conjugate pairs. Okay, these are known as conjugate pairs. Okay, so as I already discussed this, time and energy are conjugate pairs. with the joule second unit, the product of measurement error in the is given by Heisenberg principle del E into del T h by 4 pi. You can find this. With this, what we can find first this thing, and then putting the value of del T. Here del T is going to be okay because 3 into 10 to the power minus 3 is given. So we know 1 joule is 6.242 into 10 to the power 18 electron volt. Why so? As you can see, if I need to find 1 electron volt, so that is 1 joule divided by 1.6 into 10 to the power minus 19. So in this way we can do that, and when multiply this thing, so we can get the answer C. Okay, now the next question is important. Okay, wait for a while. What happened to my ears today? A wet ball weighing 10.12 gram has a water of 0.1 gram on it. The ball is moving with a constant velocity with an uncertainty of momentum of 10 to the power minus 6 kilogram meter per second. What will be the uncertainty in the measurement of the position of the ball, water, and electron in the water molecule? Okay, so what we need to do, we need to find what have we? This is given velocity, right? So for water, for ball, and for electron, we need to find what? Uncertainty in measurement. So again, solution or a hint, del x measurement or basically position, del x into del p equivalent greater than h upon 4 pi. Okay, so for del p for ball, del p for water, and del p for electron, we can know because we know the mass of a water. Okay, you can find the mass of a ball alone, and then mass of electron we know. So calculate this thing, and then with this general equation A, we can find the del x just for ball. Okay, and this del x for water, and similarly del x for what beta? Del x for electron. Okay, I'm just going to write E. Same again, h upon 4 pi del p for ball, h upon 4 pi del p for water, and okay, I'll write this thing a little bit lower. Okay. 4 pi. Okay, so using this equation 1, 2, and 3 we can find it. Clear? But that is not all about. You need to give me this ratio. Ball, this water, and this electron. I want this equation number 4. Clear everyone what you need to do? Clear na? Everything is given here. So just do this, and this is a theoretical question even, and tell me the answer. See, when we need to find the ratio, so just only thing, you don't need to find the value of h upon this thing 4 pi or anything, because del x is equivalent greater than directly proportional to inversely proportional to change in momentum. So obviously the order for change in momentum you need to discuss, you need to find, and then we are going to discuss. Clear everyone? Is this clear, everyone? Okay. Do this and tell me the order. Order for this del X for ball, del X for water, del X for electron. That's what I write now. Yeah, for ball, water, and electron. Okay, this is the first. Do this and tell me the correct answer. One hundred one. 110 to the power minus 31. The minus it is not going to be there in any case. Anyone else? How it is going to be minus? not minus in power. Still a little mistake. Or hmm, almost correct, but a little mistake. 1 10 to the power 2, which is 1 10 to the power 2 left. Sudarshan, sorry sir, left. Okay, see how you can do that, how you can approach this. The same thing you need to do, same exactly, but a little bit del x into del p is h upon 4 pi, right? Velocity being constant, uncertainty. You can say velocity being constant, uncertainty in the measurement of the momentum is associated with the mass of a matter. So uncertainty of the momentum of a dry ball, mass into 10 to the power 6. So mass is 10 point something, so 10 we can take. Okay, 10 into 10 to the power minus 3 kilogram, because it is given in the gram. So into this. So 10 into 10 to the power minus 6, so that gives you basically the momentum of a ball is 10 to the power minus 8, minus 6 and minus 2. Here it is 0.1, so basically 10 to the power minus 1 itself. So what it is going to be 10 to the power minus 10, and for this the momentum is going to be 10 to the power minus 37. Okay, you can check it out. For electron it is 10 to the power minus 37. So when we find it, so basically uh, this change in displacement or change in position is directly, or sorry, inversely proportional to the momentum, because h upon 4 pi is going to be cancelled. Obviously this m is going to be cancelled. Okay, then 1 by 10 to the power minus 8, 1 by 10 to the power minus 10, 1 by 10 to the power this 9 is going to be cancelled, so 10 to the power minus 36. So taking 10 to the power 8 common, 1 ratio 10 to the power 2, 10 to the power 28 is going to be there. So that is your correct answer. Okay, so let's here, because it is already done, so let's take a break for 5 to 10 minutes, and then we are going to discuss this and Davisson germer experiment. Clear beta? Hello, 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 hello. Just a minute. Am I audible? Hello, hello, hello. Am I audible, everyone? Right? Yes. Okay, beta. Just a minute. Yes. So whatever we learned till now, na, this uncertainty principle, this de Broglie wavelength hypothesis, and everything regarding the matter wave, we are going to prove, and we are going to prove, but we are going to see an experiment which is going to prove that, and that is known as Davisson and germer experiment. What it states that we are going to see in the next class, but we already done this in the previous class. So let's quickly recap this. Photocell, what it is? It is a device which converts light energy into electrical energy. It is also called an electric eye, as the photoelectric current setups in the photoelectric cell corresponding to the incident light. It provides the information about the object as has been by our eye in the presence of light. A photo cell consists of a semi-cylindrical photosensitive metal plate C. This is going to be emitter, and a wire loop A. Okay, this wire loop A, collector supported in a evacuated glass or quartz bulb. Why it is going to be in evacuated glass or quartz bulb? I already discussed this thing in the beginning. When light of suitable wavelength falls on the emitter C, photoelectrons are emitted. Okay, this is simple thing. We already discussed this thing. So let's focus on to this Davisson and germer experiment. So what it is? First of all, as you can see this, so basically I am going to describe each and every particular aspect. So this is vacuum chamber. Again, what is a vacuum chamber? Why we required a vacuum chamber? Because if you don't have a vacuum chamber, so single electron in the presence of light or in the presence of O2 can burn or can get a fire. So that is why we need this. Okay, see, this thing is a movable detector. What it is? It is going to change its position from this particularly, from extreme points A to B. So whenever from the heated filament, an accelerated anode basically, or you can say a charged particle is going to be hit this nickel target. So this is going to give you the diffracted electron beam. This is going to give us the photoelectrons, and photoelectrons are not going to be given in that one direction, one liner, right? So it can be here, it can be here, it can be here, it can be here, it can be here. So the meaning of this movable detector, or the sense, or you can say the application of this movable detector is it is going to move with the time, and in a specific range it is going to detect however wherever we get this particular photoelectrons. Is this clear, everyone? Is this clear na? This thing, whatever I just say, okay, basically from the matter wave. So movable detector is continuously moving, or you can say a detector moves continuously, or you can say moving continuously, continuously, NUOUS. Yeah, and that is your vacuum chamber. We know what we already know, everyone, what a vacuum chamber is, okay, and why it is required, and why this movable detector is required. Generally, you can say easily to understand, because wave we want to get, or we get photoelectrons in the you can say in terminology of wave characteristics. Wave, heated filament, what it is? When you heat any particular filament, so it gives you the number of electrons, it gives you the basically the charge particle. So from here we get the charge particle. Why is accelerating anode? This accelerating anode increase the increases it basically increases the energy or kinetic energy of charge particle, kinetic energy of moving charge particle. Obviously they are moving with some energy, moving charge particles. Got it, beta? So yeah, so they are moving with some energy, but this anode, or you can say accelerating anode, the name itself defines accelerating, means anode is a positive thing, and whenever we suppose the charge is basically electronic charge, negative charge, so whenever a positive charge is going to capture it is, so it is going to increase its speed, its kinetic energy. And this is electron beam. Again, this electron beam is going to hit this nickel target. Basically this nickel target is going to give the matter wave. Okay, diffracted electron beam. This electron beam is going to diffracted, and we are going to see a matter wave. Okay, this is basically happening here. Now the characteristic, and you can say in this particular not characteristics, the prerequisite thing, or you can say the necessary points, the necessary thing, the necessary conditions for Davisson and Germer experiment are this. Okay, so an electron gun comprising a tungsten filament F was coated with a barium oxide and heated through a low voltage power supply. So this particular thing, which is a heated filament, in this we containing this barium oxide and heat through a low voltage power supply to give the electron beam to generate, to find the matter wave. While applying suitable potential difference from a high voltage power supply, the electron guns emitted electrons which were again accelerated to a particular velocity, because until unless it is not going to accelerate it through a particular velocity, so they just hit and they are not going to diffract, they are not going to give us the matter wave. In a cylinder perforated with fine holes along its axis, these emitted electrons were made to pass through it, thus producing a fine collimated beam. What does it mean? They are just you can say this accelerated electrons going to be in this direction, in this direction, in this direction, right? But they are made to pass this accelerated anode to increase its speed and to make a beam like a photo, you can say, like whenever we turn on the torch, so we can see the beam of a light. In a same sense, the beam of electrons we required to get the matter wave whenever it is going to hit this target, which is nickel target. Okay, the beam produced from the cylinder is again made to fall on the surface of a nickel crystal due to this electrons scattered in the various directions. Till now we just reached to this process. Now the next process is important. Got it, everyone? So these are the prerequisite thing, or you can say necessary condition for this experiment. Explanation for the necessary conditions, because these conditions are required. Okay, this one, this one, this one, and this one. Clear, everyone? These basically whatever I draw or whatever happening back then in the this particular experiment, I am trying to explain that. Okay, so these were the necessary conditions and prerequisite things. Moving moving ahead, the beam of electrons. Okay, this one is going to be important. The beam of electrons, the beam of electrons produced has a certain amount of intensity. Obviously, whenever the beam of this electrons is going to be produced after passing through this accelerating potential, accelerating anode, so they have a certain amount of intensity which is measured by the electron detector, and after it is connected to a sensitive galvanometer to record the current. It is then moved on a circular scale. Okay, after when it is going to hit, so this movable detector is going to attach with a galvanometer, and what galvanometer does, galvanometer gives us the small amount of potential difference as well as the current. Okay, by moving the detector on a circular scale at a different positions, that is changing the angle, that is theta, changing angle theta, angle between the incident and the scattered electron beam, the intensity of the scattered electron beam is measured for different values of angle of scattering. What does it mean? As this electron beam is going to hit with this, so if it is there, so angle is going to be this. Meanwhile, if this scattered electron is going to be this, right now I have this detector here, so the angle is going to be less. But if the detector is going to be there, so the angle is going to be more further away, right? So changing in the angle, what is going to be the effect, we are going to see. Clear? Clear na? For the given diagram, angle is this. For I mean what I draw with this dotted line, the angle is this, very less, and from you can say for the farthest point B, the angle is more. So we are going to see the change in intensity, basically the change in current, the change in diffracted electron beam current due to this different angles, and that is value of angle of scattering. So the intensity I of the scattered electrons, by changing the angle of scattering, theta, by changing the accelerating potential difference, the accelerated voltage was varied from 44 volt to 68 volt. Okay, but these all things are the conditions. We are not putting anywhere. You can say we are not putting by ourselves. You can say from any particular textbook. But these are the conditions what back then Davisson and Germer put and situated and make to complete this experiment. This 44 volt to 68 volt, this angle varying from 50 degree, or you can say at 54 volt we get the maximum. We could see a strong peak in the intensity. So this everything whatever is written over there is the condition, the result, the process, the method what was done by the Davisson and Germer during their experiment. Clear na everyone? It is not might be, you can see the slight changes in these values from first book to another book, or you can say from one book to another book, but the general major thing is going to be the same. Like potential is going to be 54 volt. The angle where you get the maximum piece is always going to be 50 degree. Okay, and with the help of electron diffraction, the wavelength of matter was calculated 0.165 nm. Nm stands for nanometer. And as you can see, 0.165 is almost okay. Nm is basically 165 into 10 to the power minus 12 meter range. Got it? So we are going to see how we get this. Again, I am telling you, this is all the things the Davisson and Germer did in their experiment. Got it? Experimental data it is. You cannot change, you cannot put something else other than this. Clear everyone? Okay. So the intensity I of the scattered electrons by changing the angle of scattering, we need to see by changing the accelerating potential difference, the accelerated voltage was varied from 44 volt to 68 volt. Means if we changing the potential difference, the voltage is varied from 44 volt to 68 volt. With the intensity I of the scattered electron from for an accelerated voltage of 54 volt at a scattering angle theta 50 degree, we could see a strong peak in the intensity. Means we get the in maximum intensity at two particular point. I max we get at potential difference which is 54 volt. What potential difference is this? Accelerating anode potential difference, and theta scattering angle is 50 degree. So at this particular conditions we get I max. Okay, rewriting this statement, we get I max means V means this experiment, we get I max, intensity max at potential difference this, and theta is this, and this is again I am saying the data from the experiment. This peak was the result of the constructive interference. Okay, obviously we get the peak wherever the constructive interference is going to be. So this peak was the result for the constructive interference of the electrons scattered from different layers of regularly spaced atoms from the crystal with the help of electron diffraction, the wavelength of matter wave, because it is diffraction of electrons, because we initially incident the electron beams. So this electron diffraction which gives us the matter waves or wavelength of matter waves was calculated to be this much. How we can calculate, that is on the next page. So according to this de Broglie or de Broglie hypothesis, we know this lambda equals to h by p. We also know lambda equals to h upon 2me, where E is kinetic energy, and we also know h upon 2mev, because E kinetic energy here. Okay, this is our kinetic energy, and we can put this kinetic energy into the form of electron volt. Simple as that. Where m is the mass of electron, E is charge of an electron, and h is Planck constant. Then moving ahead, putting everything value. Therefore, for a given volt, for a given potential difference, for an electron, we'll have a wavelength given by equation 1. the following equation from the Bragg's law, n lambda 2d sine theta minus this. Okay, what it is, there is a law which you're going to see in the higher classes, or you can say this is basically diffraction in matter. Okay, so Bragg's law, okay, small detail about it, not much. Bragg's law gives, or you can say it gives the relation, it gives it gives the relation, between, it gives the relation of a matter waves, of matter waves same as diffraction. Okay, what is the diffraction maxima and minima condition? Anyone? Anyone? What is the diffraction maxima and minima condition? Just minima, you tell me, because that is written over there already. Maxima diffraction minima condition is A sine theta equals to L lambda, right? This is the maxima condition, na? Where A is the distance between two slits, or you can say clear width. So in a same sense, D here is you can say distance between two crystals. Crystals is like, I mean, there are so many things like FCC, BCC, and maybe or might be you learn, read or hear these terms in chemistry. Simple cubic crystal, body centered crystal, face centered crystal, right? You hear this terminology in chemistry now. Okay, so in a same sense, the distance between two crystals where the electrons is going to be situated. Okay, for simple cubic, suppose there is a one cube. On each particular corner we have a okay, what it is happening over, see, there is a crystal. In this way there is going to be arrangement, right? If I draw another this particular unit cell, this is basically known as units. This is basically known as unit cell. If I draw this, okay, just a minute. Which color I choose? This. Okay, so the distance between two unit cells is basically D here. This distance, it is okay. Not this color is not visible. Sorry. This is the distance between two unit cell. The same, the distance we can observe in between two slits, right? So whenever light is going to be interact, whenever light is going to be hit this photon, or you can say from this particular motion of matter or this electron beams, we can get this lambda or matter wave. Clear, everyone? Means I'm just trying to give you a simple, you can say, arrangement. Suppose a simple cubic arrangement is there, and obviously simple cubic is going to be different at different point of you can say this particular, any particular crystal. And if I'm going to hit, or if I'm going to incident electron beam, so this electron beam is going to give the matter wave of diffraction, basically electron beam diffraction. So electron beam diffraction is going to follow the same rule for a diffraction. The rule for a diffraction is, in general, what it is, for a minima condition, n sine theta, or you can, sorry, this a sine theta is going to be n lambda, right? So in the same sense, the following equation gives by the Bragg's law, and we can learn about this more in graduation in which particular solid physics. Yeah. Okay. In solid state physics, we learn about more these particular things, matter, waves, and so, and the basic structure of solids. So from there we can get this relation n lambda equals to 2d sine theta, 2d sine 90 degree minus theta by 2. So for wavelength, sorry, for potential 54 volt, okay, for potential 54 volt, simply I know this relation. For potential, I mean, we know this relation, 1.228 nm nanometer divided by volt. So if I'm putting this volt here, 54, so we can get this relation. Okay. Somewhere on the previous page, wait, there is a relation, this, wait a minute, beta. Yeah. So here you can write it down. This is 10 to the power minus 9. Okay. Just a minute. Values or power you can check, 1.2228 nanometer. Nanometer means 10 to the power 9. Power you can check. This is the correct relation. And this is written over here. Clear everyone? This thing till now. So this is again an important thing. Clear beta everyone? Clear na? Okay. If it is clear, so this is your question. Assisted practice related to this. Okay. I need to explain this. So the mass m of two particles x and y are such that mx is going to be greater than my. If both the particles have same de Broglie wavelength, then it is very easy. De Broglie wavelength is h upon p. Use this concept. P is mv. Tell me beta which option is correct for this. A, B, C, D. Which one? Everyone got C or not? See, that is very easy. We know that de Broglie wavelength is this. I already tell you the answer. So let Px and Py be the moment of n x and y respectively, and lambda x and lambda y be the de Broglie wavelength of x and y. So lambda x and lambda y is given. H is a constant thing, so Px and Py is equal. Therefore, their momenta are same. So the C option is correct. Everyone, is this clear or not? Pavan, Darshan, Sai, are you there, beta? Yajira, Vishwanath. Okay, this is the next. The ratio of the wavelengths of the monochromatic light A to the monochromatic light B is 1:2. Wavelength ratio is given. Find the ratio of their momentum. Very easy. Again, more basic to basic. Which one option is correct? This is more easy. It is more easier than the previous one. Everyone got A. See, that is very easy. The ratio of lambda A to the lambda B is 1:2, and we know lambda is h by p. So lambda of A inversely proportional to P by A. Similarly, lambda of B inversely proportional to P by B. Okay. So then the correct answer is yes, it is 2:1. Okay. Don't if I mean if you have a you can say proper theoretical answer, so you can write in this long way. But for MCQ you don't need to. Or subjective answer. Explanation or subjective or explanation to write subjective answer. Subjective answer. Clear, beta? Means if you need to write subjective answer, so that is given this del A by del B is 1/2. We know the relation momentum of a photon P equals to h by lambda, or simply using this hypothesis lambda equals to h by p. H is constant, so you don't need to worry about it. Then Pa equals to h lambda h upon lambda A. Similarly, Pb is h by lambda B by equation 3 and 4. Pa by Pe is going to be lambda B by lambda A and 2 by A. So the correct option is this. Okay. You can do this in a 2-line also, but for objective thing. For subjective thing, you need to write. Okay. Clear, everyone? Okay, so in this way, we complete this particular chapter. The next class is going to be the DRS one. Okay, so in this particular class, first of all, what we done, the important things, wave nature of a light, or Heisenberg uncertainty principle, photocell, Davisson and germer experiment.